Over the next couple of sections, we look at some circuit concepts that can be used when you're building or designing a balancer. And in this section, we look particularly at passive balancing circuits. Now, I've used the term passive and active balancers before, and now we're going to begin to explore really what that means in terms of a topology or an electronic strategy. And this chart shows some of the ideas that are common in cell balancing systems. So at the top we have, okay, I want to do cell balancing. How am I going to do it? The passive methods are going to dissipate the energy as heat. They're not making any attempt to actively move energy around. They're just kind of passively dissipating energy. In this section, we look at three methods. One is a fixed shunt resistor, one is a modified version of a fixed shunt resistor, and the other is a switched shunt resistor. And again, what they have in common is that the energy is dissipated as heat. Active balancing systems, I'm trying to move energy around from a strong cell to a weak cell in some sense. And the two basic methods use the two reactive kind of components of capacitors and inductors. Charge shuttling is what we call it when we're using capacitors. We'll look at that in the next section. And energy converter is what we think of it when we either have a combination of capacitors or inductors or inductive methods alone. Looking first at the absolute simplest balancing system that's possible is this idea of a fixed shunt resistor. Here is the battery pack design. So you see that we have a lot of cells. There's the positive terminal, there's the negative terminal, and in parallel with every cell we have a resistor that is permanently physically connected. And this is a high value resistor. This is a big resistor. If it's a small resistor, I've got essentially a short circuit around the cell. And that would be a very poor thing to do because I wouldn't be able to hold very much charge for very long. So we have a large valued resistor in parallel with every cell. The idea is if I have a cell with a high state of charge and a cell with a low state of charge, the high state of charge cell is going to have a higher voltage. So if I look at, and this is SOC and this is voltage, and somehow I've got some plot that looks like this, well, the higher state of charge has a higher voltage than the other one does, and if these resistors are all the same value, then the current through this resistor is going to be higher than the current through this resistor. And that's going to bring this state of charge down, I guess I should draw it that way, faster than this one, but they are both going down. So this one's going down slowly, that one's going down quickly, and because this one's going down quickly, it's going to follow this line, and it will go from there to there, whereas this one moves not as far and only goes from there to there. And there is a self-balancing effect if I were to do this. Now the balance point here is when the voltage is zero. That's not an especially useful balance point. So we have to take great care if we're going to use this battery pack that we're always having this pack in we're never leaving it unattended for long periods of time because it could self-discharge through this external resistor down to zero. This design is probably most appropriate for something like an uninterruptible power supply, which is almost always fully charged except when it's needed. And this fully charged nature allows the voltages of these cells to so I have an external voltage in the pack here that's keeping it charged most of the time, and that's going to then make it not matter that I'm dissipating some charge some energy as heat through these resistors, and they'll all be balanced to each other. And then when I need when the external voltage is lost and I need to supply energy from the battery pack, it's okay to have this very slow balancing still going on. It's not ideal, but it's okay because I hopefully need the UPS for only a short amount of time anyway. So this is very, very simple design, and it's always dissipating charge energy, even when the pack is perfectly balanced. A variation on this design uses Zener diodes to shut off balancing when the voltage drops below some point. And you can think of the Zener diode being, at least ideally, a switch that has very low resistance when its voltage is above some point, and a very high resistance when its voltage is below some point. So it's basically an on-off switch. So if this cell goes above the Zener diode cutoff voltage, then the diode starts conducting, and the cell is going to then dissipate through this loop. But as soon as the cell voltage goes below the Zener diode cutoff voltage, then the Zener diode stops conducting, and we stop dissipating energy through those resistors. This would typically be designed into something where the Zener cutoff is somewhere around a 100% state of charge set point. So for a lead-acid cell, maybe around 2.2 volts. And when I'm charging the battery pack and the cell voltage is above a Zener set point, this resistor path is activated. So if this cell hits 100% faster than this cell does, then this path is activated and I start dissipating charge that way. And it allows this cell here, the low cell, to catch up in its state of charge while I'm charging this overall battery pack. This design works best for chemistries where overcharge is tolerable and the cell can float. We call it a float charge, and lead acid is one chemistry for which that's true. So if I slowly overcharge a lead acid battery, it turns out not to cause any long-term harm. And there's some nickel-based chemistries like NiCads and nickel metal hydrides for which this is also true, but lithium-ion chemistries do not tolerate overcharge at all, so this would not be a good scenario to use for a lithium-ion battery balancing system. So those methods are completely passive in the sense that not only am I dissipating energy passively, but they're completely hands-off. I'm not ever turning a resistor on or off, whereas this third method that we look at does involve a decision, and it involves some electronics to make it work. So in some ways of thinking about it, you could say, well, this is an active balancing thing because I'm using a transistor, which is an active circuit, and I'm using control, which is an active decision. So fair enough, that is a valid argument. However, that's this is still called a passive balancing system in the literature, so I'm going to keep that convention and call it a passive balancer. This method is not as wasteful as the previous two because it balances only when needed. It replaces the Zener diode with some kind of a switch, which we think of as a transistor circuit. And we have a control here, which is some kind of intelligence that's turning the switches on or off. And when the switches are off, I have just a bunch of battery cells connected in series. But when, say, this switch is on, that activates this path to carry current, and that cell will discharge through that resistor and cause balancing to happen. So this design is more complicated than the previous two because I do need to make a decision. I do need to control that transistor switch. But it does give us a lot of flexibility in our strategy, when I'm going to balance and how I'm going to balance and so forth. So we're going to close switch on cells that have too much charge and allow them to drain. When I got started in this business back in the early 2000s, and we were building our own battery management systems, this balancing was one of the most complicated aspects of the design. There's a lot of high voltage involved in biasing transistors properly and so forth to get this all to work. It was a fairly tricky thing to get the balancers to work and fairly expensive. But in modern battery stack monitoring chips, such as the ones that we looked at briefly in Chapter 1, many of these chips have built-in circuitry to control the balancing. And you send the chip an electronic message that says turn on balancing for cell number 5, and it will do so, and then turn it off and it will do so. And all of these electronics are built in, and it makes it much easier and much less expensive than it used to be. So these chips sometimes have internal transistor switches, so you have an external resistor and an internal switch for slow balancing, or sometimes they even have an internal resistor for very slow balancing, or sometimes they just have a pin where they have a gate drive for an external transistor to do the faster balancing. It's still passive balancing, still dissipating, but I can have a higher current using an external transistor and resistor than I can with an internal one. When we're looking at any of these passive balancing systems, the primary advantage compared to active balancing is simplicity and therefore cost. And cost is a big deal in a lot of applications compared to this active balancing design. And when we do our homework project on this, you're going to investigate if all I want to do is to keep cells balanced at a top state of charge. We're probably going to find that passive balancing is enough to do it. If I want the additional benefits of maximizing power and energy and things like that, then active balancing is going to have an edge. But you have to decide if the added cost is worth it for you. So there are some drawbacks. The advantage of passive balancing is simplicity, but the drawbacks are listed here. One of them is that I'm wasting energy as heat, and I could be using this energy productively, or at least most of that energy productively, and that just seems wrong. If we employ a design that balances at a top state of charge, then I'm going to be leaving energy in cells when the weak battery cell is completely discharged, and I could have used that energy if I had an active balancing system. So again, I'm not wasting energy in the same sense that I'm just dissipating it, but I have unusable energy stored in the battery cells. This heat is also an issue. Power is dissipated as heat is the nominal voltage times the imbalance current, or the balancing current of the cells. And if I want to balance quickly, I have to crank up this balancing current, and more heat is going to be generated in doing so. One thing that does, we know that power also is I squared R, and if I select a resistance to accomplish the balancing current that I want, then I figure out what is the power rating of that resistor. We'll find that it's often a high wattage resistor. It's not like an eighth of a watt. It's probably more like a watt or 2 or 3, depending on how quickly I need to balance. And those are big resistors. They're expensive resistors compared to just a normal resistor. So the resistor itself is not as inexpensive as you might think. And the transistor switch that controls it has to be able to control a fair amount of current also, so it may not be as inexpensive as you would think. And also, the heat that I'm generating by passively balancing can be similar in order of magnitude to the heat generated just by normal cell operation. Even though I'm passing hundreds of amperes through battery cells, they have resistances on the order of a milliohm, whereas I'm passing much less current through a balancing resistor, but it has a higher resistance than a milliohm, and overall the total heat may be very similar. And we have to factor this into our design of our cooling system. that I have to be able to take away a certain number of watts of heat from normal operation, but also from balancing operation. And the thermal management system is a significant expense in the battery pack. It's not a small expense. And if I had to double its size, that's a big design consideration. And finally here, if I do passive balancing, the battery pack life might end up being shorter compared to a pack where I do a clever active balancing design. The pack life is determined by the weakest cell, and in an active balancing scenario, we've said that we can intentionally place more stress on strong cells and less stress on weak cells to bring the cells together into a more homogeneous or more uniform end-of-life configuration. So if we think about cell performance over time, they might all start the same, but suppose I've got a weak cell that does that versus time and a strong cell that does that versus time. The pack life is determined by when my weak cell hits my limit, my design limit. If I can stress the strong cells in order to take stress off the weak cells, I get a behavior that's more like an average cell behavior. So overall, the life is here instead of there, and the overall length of operational use of the battery pack is longer. So some things to think about. There's pros and cons. The biggest advantage of passive balancing is its simplicity. But there are these disadvantages that you also have to consider in a design.